what happens in case when you have, let us say, magnetic field in this direction, as you can see in this direction, and we have in x, y, z, so it's easy for me to communicate. So the magnetic field is along the positive x direction, and the charged particle is moving with a velocity v subtending an angle theta. In which plane? That is very, very important. In which plane? In xy plane only. Alright, so the charged particle is moving in xy plane, subtending an angle theta. Then what happens? See, can I just break down this velocity vector into its two components, one along x, that let me call this as v parallel, and one along y, right? Two mutually perpendicular direction I can break this vector into, right? So let's call this as v perpendicular, no problem. Okay, so v parallel is also there and v perpendicular is also there. What will be the value of v parallel, by the way? This will be v cos theta. And what will be the value of v perpendicular, by the way? V sin theta. When I say parallel or perpendicular, I mean with respect to the magnetic field, of course. All right, so there is a component which is parallel to the magnetic field, okay, and there is a component which is perpendicular to the magnetic field. Okay, so now again this person who is the magnetic field, he comes and he sees, okay, so you are a charged particle, right, and you are trying to move in my region. Okay, let me check your velocity first. Oh, you have a parallel component. Okay, go ahead, I won't disturb you, you are traveling parallel to me. Oh, wait, there is also a perpendicular component. Perpendicular component, right? I'll make you move in a circle. So this is what happens. All right, so it will be an amalgamation, it will be a mixture of a straight line motion and a circular motion. How is that going to look like? Obviously beautiful, but how and what is this called? All those things we are going to understand now. So what we have told is that, okay, we have got this a charged particle and we have broken it down into two components. One is the parallel component, another one is the perpendicular component. So if I just talk about this will be my perpendicular component, v perpendicular, and if I talk about this will be my parallel component, or v parallel. No problem. Okay, now when the magnetic field sees it, it looks at the two components and it says, oh wow, you have a perpendicular component, don't you? Which means I'll make you move in a circle. Now the direction in which the force will be applied can be found out easily. You can use the left hand, correct? The magnetic field is along x. The velocity is at some angle, yes, but I'm only talking about the component because of which it is moving in a circle. So that is v sin theta. So along x. So you can see the force is like this, isn't it? So because of that, it will start moving in a circle. No problem. Okay, but it has also got this v cos theta, no? So it will move in a circle and will also shift, because v cos theta is not being affected at all. Move in a circle and will also shift. Move in a circle, will also shift forward. Did you understand? Move in a circle, but shift. Go on shifting. Did you understand this? All right, so this is the net motion. It's a amalgamation of, or a mixture of, two motions. One is a circle, another is this linear motion. So at the same instant, it has to do both the things, correct? Because of v cos theta, it has to go forward, as well as because of v sin theta, because this component is perpendicular to the direction of the magnetic field. So there is a force which is applied, and this force is making it move in a circle. So this is how, like a spring, this is how you will see the trajectory looks like. All right, okay. So you see what happens. What happens is that because of this, there will be a force, and because of this force, there will be a circular motion. Because of which component? Definitely perpendicular component. What will be the radius of this? R is equal to, we know, mv perpendicular divided by qb. What is the value of v perpendicular, sir? Well, v sin theta. So we get the value of the radius of this circle to be equal to mv sin theta by qb. No problem. All right. So had this been only perpendicular, the velocity would have been perpendicular to the magnetic field, then it would have just moved in a circle. But it has got one more component, isn't it? There is one more component because of which it also has to move forward. It also has to move forward like this. Because on this, or because of this horizontal component, or the component which is along the magnetic field, okay, there is no force, right? There is no force. if there was only one velocity which is along the direction of magnetic field would not have cared. You would, okay, you are parallel to me, go, no problem. Okay, you are perpendicular to me, move in a circle. Okay, you are both parallel and perpendicular. Okay, so now because of this perpendicular component, I'll make you move in a circle, and because of this parallel component, you also have to go forward. So do that. Go in a circle, move forward. Go in a circle, move forward. Go in a circle, move forward. All right. So if you talk about this, what happens actually is the motion looks something like this. The motion looks something like this. One, you can see how it is moving in a circle. Another one, you can see that how it is, you know, making a path like this, which is called as a helix. This is a helical path. All right. So the motion is like this. This is how the charged particle starts moving. It has to move in a circle as well as move ahead also because of this component of v cos theta. So it starts moving like this, and then this path is what we call as a helix. All right, the easiest example to understand this looks something like a spring, doesn't it, right? So something like this, no problem. All right, now there are certain terms that you need to take care. Obviously the radius of the helix will be equal to mv sine theta by qb, because the circular motion is only because of the perpendicular component. Clear, sir? Yes. All right, the circular motion is only because of the perpendicular component, and the linear motion is only because of the parallel component. All right, so a combined motion will be a circle and then moving ahead. All right, okay, so this is called as a helix. Now what will be the pitch of this helix? What will be the value of the pitch of the helix? So you see, what is pitch? Pitch is this distance. All right, pitch is how much has it moved along the direction of magnetic field, this distance. Now why it is moving along the direction of magnetic field? Because of which component? Because of which component? It is moving along this because of v cos theta. All right, so it is keeping on moving. So what should I call a pitch? Is this a pitch? Is this a pitch? Is this a pitch? So the amount of distance it has moved in one time period along the direction of magnetic field is what we call as a pitch. Did you understand? The amount of distance it has moved in one time period, the time taken to complete one circle. We know that, how to calculate it, isn't it? Because we have all the formulas, isn't it, right? Correct. So we know the formula of time period. We know the formula of time period. And what was the formula of time period? Time period was equal to 2 pi m by qb. So in this much time, how much does it move along the direction of magnetic field in one time period? How much it is shifting? How much does it move in one time period? That distance is what we call as pitch, which means the pitch, let me write it as P, will be what? Velocity times the time period. What is the velocity? Which velocity? V parallel, right? So pitch will be v cos theta times 2 pi m by qb. No problem, right? So this will be the value of the pitch, which is 2 pi m times v cos theta divided by qb, and this distance is called as the pitch. You see, this is one time period. One time period. All right, the time taken to complete one circle, in that much time, how much does it move along the magnetic field? How much does this charged particle move along the magnetic field will give you a value of the pitch. As simple as that. All right. Okay. So yes, another important formula to remember. Yes, it's just a formula that you can easily derive. So this would be a case when the velocity vector is at some angle with the magnetic field vector such that it has got both the components. All right. One perpendicular component will become the reason of this charged particle moving in a circle or a circular motion, and the component which is along the magnetic field or the parallel component will become the reason. Why? Because why it is shifting along the direction of the magnetic field. Hence we are going to see a net combined motion. Well, the path that we see is called as a helical path. All right, and the distance traveled, all right, the distance traveled in one time period is along the direction of the magnetic field is called as what? Is called as the pitch. And this is how we can calculate the value of the pitch. Clear with this? Okay.